Students, we will today study about a capacitor. Okay. The capacitor, actually, the structure of a capacitor is like this. You have a metallic plate like this. Okay. And you have another metallic plate. Two metallic plates are there. And these two conducting plates, you have this is a conducting plate. And this is also another conducting plate. There are two conducting plates. And these two conducting plates are separated by a dielectric. What do you call a dielectric? Or you can call it as an insulator also. You can call it as an insulator, electrical insulator. Okay. So this is what you have for a capacitor. And the symbol for a capacitor is given by like this. This is the symbol for a capacitor. And the unit of a capacitance is given by unit of capacitance is farads. Represented by the symbol F, right? Now what does the capacitor do? The capacitor stores energy in an electric field. That's what the function of a capacitor. Okay. The capacitor stores energy in electric field. Okay. So you can see inductance stores energy in a magnetic field, right? Inductance stores energy in a magnetic field, but the capacitance stores energy in electric field. For example, if I am connecting a capacitor like this, okay, to a voltage source, I'm connecting it to a voltage source, right? So this is our capacitance. What happens is the capacitor charges. Okay. So you are applying a voltage V. Okay, you are applying a voltage V across the capacitor. So there will be a charge built up on the capacitor. A positive charge of plus Q will be here, and a negative charge of minus Q will be here. That's what happens. So the magnitude will be same on both plates, but the sign will be different. Okay, so there is a relation between the applied voltage, the capacitance, and the charge stored on the capacitor. This relation is given by Q equal to CV. It's a very important relation in a capacitance. Okay. For a resistance, you have already known about the Ohm's law, where you have V equal to I into R. Similarly, for the capacitance, you have Q equal to C into V, right? That's the relation. Now you see, you have Q equal to C into V, right? Isn't it? So what will be the current? You know the current is, from this you know I equal to the rate of change of charge, right? I will be dq by dt, right? So you can write it as C dV by dt, right? That's a very important relation for the case of a capacitor. The current is given by C dV by dt. I think this is clear to you, right? So that is a charging current. Okay. Okay. For example, if you have a capacitor like this, okay, and if the applied voltage is plus minus V, and you have the current I like this, right? Okay. Then I is positive. Okay. I positive and that is charging. That is the convention that we are using. Okay. So when V is constant, you have I will be equal to 0, right? When you substitute into this particular equation, you know when V is constant, dV by dt will be 0, so I will be 0. That's how you will find out. Right? Now, next, you know I equal to C dV by dt for a capacitance, right? Right. Now, what will be V from I? So if I is the derivative, V is obviously the integral, right? So you can write V equal to 1 by C integral T0 to T, okay, I dt plus the initial voltage V T0. That's our general equation for the voltage of a capacitance, right? Okay, when T0 is equal to 0, you can write it from 0 to T, right? When T0 equal to 0, you can write it as when T0 equal to 0. And if initial voltage Vt0 equal to 0, you can simply write V equal to 1 by C integral 0 to T I dt. Okay, you can write it like that. So now we will see what is the power delivered to the capacitor, right? You know the instantaneous power delivered at any instant the power, you can write instantaneous power delivered to the capacitor is P equal to V into I equal to C dV by dt is I, right? So you can write it as C into V into dV by dt, right? Understand? That is the power, and you have the energy stored, because you know energy stored in a capacitor. Energy stored in a capacitor is given by W equal to half CV square. That's the energy stored. Okay, so these are the equations for the power and energy. Okay, this energy can be written in these terms also, Q square by 2C. Both are same. Both equations are valid. You can have half CV square as well as Q square by 2C. These two equations are valid. Now we will do an example. You have an example here. Okay. You have a 3 picofarad capacitor. A 3 picofarad capacitor, right? With 20 volt across it. You have a 3 volt capacitor with a 20 volt across it. So the question 1 is, calculate charge stored in it. Charge, you have to calculate the charge stored in it. Okay, what's the charge stored? You know, charge is given by Q equal to C into V, right? C is 3 picofarad. That is 3 into 10 raised to minus 12 farads, right? 3 into 10 raised to minus 12 into voltage is 20, right? So that will be equal to 60 picocoulombs. 60 into 10 raised to minus 12 coulombs, right? And the second question, question B is like this. Find energy stored in the capacitor. Find energy stored in the capacitor. The second question. Okay. You know the energy stored is given by W equal to half C into V square, right? So that is half into 3 into 10 raised to minus 12 into, right, 20 into 20. So you will get it as something around, that is actually 600 picojoules. That's energy stored. That's how you will do the problems for finding out the charge stored as well as energy stored in the capacitance. So in fact, you can connect capacitors in series as well as parallel. We will see what happens. So capacitors in series. First we will examine capacitors in series. Right. For example, if I am having capacitors C1, C2, C3 like that, Cn, okay, this is C1, C2, C3, all of them are connected in series, right? I am connecting them to a voltage source here V, okay, and I connected all those capacitors in series, okay. So I can in fact make an equivalent circuit like this, V, okay, plus or minus, plus or minus, okay. You can have an equivalent capacitance, C equivalent, like this, right? The voltage from here to here is V1, from here to here is V2, from here to here is V3, and from here to here is Vn, right? So you see, from here to here you have V now. You can write 1 by C equivalent equal to 1 by C1 plus 1 by C2 plus 1 by C3, like that to 1 by Cn. Okay, that's the rule. Or else you can write C equivalent as, okay, you can write C equivalent, you can write C equivalent like this. C equivalent can be written as 1 by C1 plus 1 by C2 plus, like that to 1 by C equivalent. That's also possible. You can write like this also. Mm. And you can write V equal to, you can also write V equal to V1 plus V2 plus Vn. Right. So that's about the capacitors in series. It's the same law that you have for capacitors in parallel. And if you have only two capacitors, right? If you have only two capacitors like this, and you're connecting it to a voltage source, okay, C1, C2, you can write C equivalent equal to C1, C2 divided by C1 plus C2. That's in parallel, right? For two capacitors, right, in series. When you have two capacitors in series, you can simplify the rule like this. Similar to the rule that you have for resistors and inductors in parallel, right? Now we will examine the condition for capacitors in parallel. For example, I have a current source like this, I, right? I have a current source I. Connector capacitors. C1 to Cn in parallel. Okay. You can represent it by an equivalent circuit like this. I, and this is an equivalent capacitance, C equivalent, right? So this is I1, I2, the current I3 going here, and you have one going IN going here. You can write I equal to I1 plus I2 plus I3 to IN you can write. And you can write a C equivalent equal to C1 plus C2 plus C3 to Cn. So this is like the law that you have for inductors and resistors in series. Capacitors in parallel, the equivalent capacitance actually is something like the law that you have for resistors and inductors in series, right? Then you simply add it up. So shall we do another problem? What I have is, I have a capacitance of 20 microfarads here. I have 20 microfarad. And then another 5 microfarad. Then you have a 6 microfarad here. Okay, it is 6. Then you have another 20 microfarad. Then you have another 60 microfarad here. I want to find out the equivalent capacitance between this terminal A and B, right? What you can do, you know that 20 and 5 are in series, right? So you can, in fact, for solving this problem, what you can do is, you can find out the series of 20 and 5. That is given by 20 into 5 divided by 20 plus 5 equal to 4 microfarads, right? So now you can simplify the circuit like this. You have a 4 microfarad here, right? Then you have a 6 microfarad here, right? Then you have another 20 microfarad here, right? And you have a 60 microfarad here. That is A, B, right? C equivalent. Now you can see 4, 6 and 20 are in parallel. So they can be simply added together. 4 plus 6 is 10. 10 plus 20 is 30, right? So now you can have, a 30 microfarad here, right? Then what else? 30 and 60 microfarad here. That is the C equivalent, right? Now these are in series, so you can find out C equivalent equal to, you can find out C equivalent equal to 30 into 60 divided by 30 plus 60 microfarad, right? So that's 1800 by 90, 90 into 2, okay, that is 20 microfarad. That's the answer for this particular question. So it's a simple problem that you can do very easily. Now I will see another question. We'll write another example 3. Example 3, you are given a voltage pulse. Okay, you are given a voltage pulse Vt with the conditions given like this. I have Vt equal to 0 for t less than or equal to 0 seconds, and Vt equal to 40 volts. Vt equal to 40 volts for 0 second less than or equal to t less than or equal to 1 second, and Vt equal to 4 e raised to minus of t minus 1 volt for t greater than or equal to 1 second. And I am given the capacitance as C equal to 0.5 microfarads. Okay. So I will first find out what is the capacitor current. The first question. You know I equal to C dV by dt, right? But you see, for different times it will be different, right? It will be V0 for t less than or equal to 0. dV by dt is obviously 0, so you can write it as 0 for t less than or equal to 0 second, right? Isn't it? And for 0 less than or equal to t less than or equal to 1 second, right? For this, actually, you have it is 40, if you take the dV by dt, 40 is V, right? dV by dt is then 4, right? So you'll get it as 0.5 into 10 raised to minus 6, that is. For 0.5 into 10 raised to minus 6 is C, right? And dV by dt is 4, right? When you differentiate 40, then you will get it as 4, right? So it will be 2 microampere, right? So it will be 2 microampere for 0 less than or equal to t less than or equal to 1 second, right? And for the third condition, you have Vt equal to 4 e raised to minus of t minus 1, right? For t greater than or equal to 1 second, right? So you can write it as 4 e raised to minus t into e raised to minus 1, right? So if you differentiate it, dV by dt, even though e raised to minus 1 is constant, you can write it as 4 e raised to minus 1 into minus of multiplied by minus of e raised to minus t, isn't it? So you can write it as minus 4 e raised to minus 1 e raised to minus t, right? Sorry, plus e raised to 1, right? E raised to plus 1, right? Okay, so that is minus 4e e raised to minus t, isn't it? So c dV by dt, current is given by I equal to c dV by dt equal to 0.5 into 10 raised to minus 6 into minus 4 into e raised to minus t, right? So the value of e, you know, what is the value of e? The value of e, right? You can find out the value of e, something around, right? Value of e is given by 2 point, so see, you can write the value of e is actually 2 point something around 718, right? E is given like this, isn't it? So you can write this as 0.5 into 10 raised to minus 6 into minus 4 into 2.718 into e raised to minus t. It's available in the calculator also, so you can find out the answer right there. So that's all for this particular lecture. I'm stopping here, and inshallah with this we end this particular chapter also. Okay, thank you all. Shukran. Assalamu alaikum.